Much, Mr. Chairman, for this nice introduction. As already has been mentioned, I would like to talk about the mechanism of dynamic embrittlement for a very specific alloy, IN718. And well, the results I'm going to present here are a part of the PhD thesis of Untitled we did 2 years ago. So he finished his PhD work already, and he was also supervised not just by me, but also from my colleague, Professor Group of the Applied University of Osnabrück. And since most people were never available for the ECF conference, I have the pleasure to present the results here. Here is the outline of my talk. After a very brief introduction, I would like to deal with the experimental details, which were a little bit specific for this investigation. I would then go into the main part of my talk, and I will show you that the loading parameters are very, very important. They affect not just the fatigue propagation rate, but also the fatigue area morphology. And we could show by means of specific tests we performed where we changed the testing conditions that the mechanism is probably a damage zone mechanism. On this basis, we proposed this mechanism and cast it into a model. And you will see the model is working quite nice, but it's necessary, of course, to obey the applicability range of the model concept. Well, so let's start with the introduction and objective of the investigation. The nickel-based alloy IN718 is a very commonly used material. It's mostly used as the disk material in jet engines, as you can see here. It's so-called gamma double prime hardened. And it is also known in the literature that it's prone to dynamic embrittlement, in particular in the intermediate temperature range around 650 degrees C in combination with the tensile stress, which is obviously a very important condition and that is undergoes in particular as a disk material. The dynamic embrittlement is normally, if you look in the literature, attributed to oxygen diffusion, which is shown here. If you have a cracked sample, the oxygen diffuses along grain boundaries into the material, and this causes a reduction of the grain boundary, as is schematically shown here, a reduction of the grain boundary cohesion, and this can lead to fast intergranular propagation. So the question we wanted to address in our investigation was how does dynamic embrittlement affect fatigue crack propagation? And well, as I mentioned already, we tried to model this effect in order to predict fatigue life as a function of the loading parameters, which are very important in the context of dynamic embrittlement. So the experimental details are that we are using a corner notch specimen geometry, which a starter notch produced by spark erosion cutting. As you can see here, the heat treatment was a normal standard heat treatment. It's a 5-step heat treatment, as you can read here, and it leads to a mean grain size of about 50 microns. The material, as I mentioned already, is gamma double prime hardened, and the fatigue tests were done under load control with a positive R value at 650 degrees C, in air and in vacuum at various frequencies and in light various dwell times. To make you a little bit familiar with our designation of the tests, if you read a test has a number 296.2, that means we increase the load within 2 seconds up to the maximum load, and then the dwell time is 296 seconds, and then we reduce the load again to the minimum load. This dwell test, of course, which is very important in the context of dynamic embrittlement. Here you see the test equipment. We use the servo-hydraulic material testing system, which is equipped with a vacuum chamber. The vacuum chamber allows us to run tests excluding any environmental effects, because the pressure is lower than 10 to the minus 5 millibar. And for monitoring break lengths, we use 2 different systems independently of each other: a 2-channel alternating current potentiometer system and a far-field microscope. And this is the reason why you see here a window in the door of the vacuum chamber. So if you look into the vacuum chamber, you see here's a glowing sample, 650 degrees C, and you see a lot of cabling and routing and wiring, and this is has to do with the ACPE measurement of the crack length. So let's come now to the results we obtained. I think the probably most important diagram I'm showing you today is this diagram, where in the normal way the crack propagation rate is plotted versus the range of the stress intensity factor. We have seen such diagrams already in the previous talks, and here are the parameters we have used, and of course, as we expected, the vacuum tests leads to the lowest crack growth rate because there is no dynamic enrichment, there is no oxygen. And if we now go into air, and if we decrease the frequency, you see the crack propagation rate increases, and if we do dwell time tests, you see with increasing dwell time, again, the crack propagation is strongly increasing. So the crack propagation area is also affected very strongly by the parameters. We have transgranular fatigue crack growth, as you can see here, at high frequencies and short dwell times. If we go to the other extreme condition, if we go to low frequencies and long dwell times, we get a very nice intergranular fatigue crack growth behavior. And well, the testing conditions we used were somewhere between these two extreme cases. So we have a fracture area where you find both intergranular areas and also transgranular areas. And this, of course, has to be taken into account in the modeling. Well, we studied this effect a little closer, and you see here evaluation of all these fracture areas we found. You see here the intergranularly felt area dyed red in order to make the difference quite clear. And you see that with decreasing delta K values and with increasing time per cycle, of course, the intergranularly failed area increases. And this, of course, indicates that dynamic embrittlement not just accelerates fatigue propagation, but the main reason, of course, is that the fraction of the intergranular crack growth increases with increasing time per cycle, as you can see here. Well, as I mentioned before, we also did some, well, I would say sophisticated tests where we changed the test conditions. This was possible because we have the vacuum chamber. And you see here as black dots here, and this blue line, one test where we changed from a dwell time test with the longest dwell time we applied to a 1 Hz vacuum test. You see here the reference lines and the reference curves. And most important here is, of course, that we found a transient behavior with an accelerated crack growth after change to vacuum. And this simply means there is obviously formed a damage zone ahead of the crack tip during the tests in air, and this damage zone is responsible for the accelerated crack growth rate after the change to vacuum. There is some oxygen in the grain boundaries, and the crack first had to propagate through this damage zone, and this is done in a very fast way. And from this and many other experiments, which I do not have the time to show you here, we tried to model the behavior in such a way that we assume if you are loading a sample with a tensile load and the sample is exposed to oxygen, you see that the oxygen is diffusing ahead of the crack tip into the material, and if you unload now and reload once again, during unloading probably nothing is happening, but during reloading then the crack is propagating along the damage zone here, and the length of this extension is exactly the length of the damage zone. And then, of course, in the next cycle, the process starts again with penetration of oxygen and so on. So one cycle after the other cycle is damaging the material. So from a modeling point of view, then it's quite simple to model the behavior, because you just have to to add the intergranular crack propagation rate with the transgranular propagation rate, and I think the specific thing here is that we are using the scaling factor, and the scaling factor B is just the surface fraction of the intergranular fracture morphology. And well, in order to show what contributions are here meant in this model, this is also very simple for the intergranular crack propagation. We assume that this is diffusion controlled, of course, and then it's a parabolic time law. T is here the time per cycle at the dwell time. And of course, the diffusion coefficient is now an apparent or effective diffusion coefficient, and depends on Kmax and the maximum value of the stress intensity factor. And for the transgranular crack propagation law, we can simply use a Paris equation with a Paris coefficient and a Paris exponent. So if we put these two equations into the equation on the top of the slide, you see that a longer equation, of course, results, but the most important thing here is that we do not need any kind of fitting. We can directly experimentally obtain all the parameters, the C values and the N values from our experimental data. And this is what I show you on the next slide. You see here, if we are using a test with the longest dwell time, this is a solely intergranular crack growth test where no transgranular crack propagation takes place. We can now, of course, take from this line the parameters to describe the intergranular crack growth, and we have the vacuum test, and this is very important here. And vacuum means there is no kind of dynamic embrittlement, so this is solely transgranular crack growth, and then we can obtain from this all the temperature we studied the Paris parameters, and the only additional parameter we need to know is this value B, which is the fracture surface fraction, which is intergranular, and this can be obtained experimentally, as I have shown you before already, or can also be calculated via a very simple approach. So spectrographic studies are not necessary here if you want to avoid that. Well, this is a comparison now. This is most important, a comparison of the predicted and the experimentally determined fatigue crack growth rates. You see the black symbols are values obtained in the experimental tests, and the red symbols, the corresponding symbols, are the model prediction, and you see that a very nice agreement exists here, because the model seems to work very nicely. But I have to say, of course, you have to consider the range of application here. And what is the range of application? We plotted here the fracture area map in a way that we plotted the delta K value here along the ordinate and the dwell time or the cycle time along the abscissa. And as you can see here, we move from a transcristally into a mixed fracture behavior. And of course, there is a very high dwell times also obtain intercrystalline fracture behavior. And what we have to consider here is that our only applicable from a physical point of view if we assume a mixed fracture morphology, and the dwell time which normally leads to a static dynamic embrittlement under sustained loading must of course be longer, and you see here the black dots, these are these dwell times must be longer than the dwell times we applied in our tests in order to keep this model valid. So we have to stay in this range, but this is for technical applications a very range. So this brings me to the conclusion of my talk. Very simple dynamic embrittlement of this material IN718 under cyclic loading condition results from the formation of a damage zone ahead of the bracket. This is our interpretation. The damage zone is a consequence of a stress-assisted grain boundary diffusion of oxygen during dwell and leads to an intergranular and fast crack propagation, at least partially or fully, and therefore the crack propagates during the cyclic part of the dwell time test that means during reloading and unloading. And with this, I would like to thank you for your attention and also Deutsche Forschungsgemeinschaft for the